Hello, my name is Haruna Gisi, and today I'll be presenting my research project called the four-color theorem. So, overview. In 1852, a famous mathematical problem called the four-color theorem was introduced when the mathematician and botanist Francis Guthrie conjectured that four colors were sufficient to color a map. This theorem is the first major theorem in mathematics that was proved using computers, and we explore this theorem in terms of graphs, and we investigate different applications of graph coloring in real life. The problem was that given a map on a plane, can we color it using no more than four colors in such a way that two regions are adjacent of each other? This problem was open for 100 years and is very easy to state and understand, but extremely hard to prove. There's a proof though, but not every mathematician is happy with it. There are mathematicians who are looking at some alternative statements, for example, involving the Birkhoff diamond, but so far the new statements are even more difficult to prove than the four-color theorem. Whoever finds the classic mathematics proof will be famous. Two examples. These are two examples of maps with four colors. The first one being the U.S. and the second one being New York. The map for U.S. is using blue, green, yellow, and red, and the map for New York State uses red, green, yellow, and brown. Note that the two neighboring states do not have the same color, meaning they are adjacent of each other and they're not touching each other. So how was it proven? In 1976, Kenneth Appel and Wolfgang Haken, two mathematicians, American and German, used 1936 maps and wrote a computer program for each one, which took over 1,000 of hours to confirm if each one of these maps can be colored by four different colors. The answer was yes. This proof introduced mathematical proofs using computers. However, not every mathematician is happy with using computers to prove theorems because in many cases it's impossible to check manually. Graphs and maps. These are two examples of graphs, also called networks. There are collections of vertices and edges connecting some or all the vertices. A map is the separation of the plane into regions that share borders. Two regions are adjacent if they share a border segment that is not one point. Graphs and maps continued. To every map, we can associate a planar graph. We associate a node to every region of the map. Two vertices are connected by an edge only if the corresponding regions share a border segment. In this case, we say that the vertices are adjacent. Coloring the regions of the map is equivalent to coloring the vertices of the corresponding graph. Not every graph can be colored using four colors. Mathematicians have been and they are still working on the problem of determining the minimum number of colors that are needed to color the vertices of a graph such that two adjacent vertices do not have the same color. This minimum number of color is called the chromatic number. Application: final exam scheduling. At some universities, the final exams are scheduled using time slots, which are assigned to each class. But two classes that have common students cannot be assigned the same time slot. This problem can be modeled by a graph coloring problem. The nodes of the graph are the different classes. Two nodes are connected by an edge. If the corresponding classes share a student, the colors represent the different time slots. One wants to find the minimum number of time slots, which are represented by colors. Application: cartography. When drawing a map, to distinguish between different countries, we need to color them with different colors if the countries share a border other than a point. To reduce the cost of printing colored maps, it was important for map makers to find the smallest number of colors needed to color the maps. It turns out that four colors are enough to do so, thanks to the four-color theorem. Application with Wi-Fi transmitters. Given different Wi-Fi transmitters in an office block all using different frequencies such that no two adjacent Wi-Fi transmitters use the same frequency in order to avoid interference. How many frequencies are needed to give a non-interfering network? One wants to know the minimum possible numbers to minimize the cost as well. So the Wi-Fi transmitters problem is similar to the four-color problem, but it is shown that we usually need more than four frequencies in most cases. These are my references. I only put down 6 references for the whole project. So any questions? Thank you.